Hello everybody, I'm Mert Imre, one of the PhD candidates working in Delft University of Technology, branch of AI for Retail Lab. My project is on manipulation of objects for retail stores and supervised by Jens Kober. Retail environments at grocery stores or warehouses include a lot of daily tasks, varying from shelf stocking to cleaning, from moving items to assisting the customers. Most of these tasks include repetition by their nature, and all of these tasks require physical effort. Some of them more than the others, as carrying materials or stocking shelves. AI has been advancing with a high pace, keeping surprising us, performing better and better every day. Our motivation is benefiting from the AI in retail, so that the robots can help with the physically demanding and repetitive tasks, and the store assistants can spare more time for the customers. Enabling robots to operate in stores includes some challenges, some of which are also mentioned by Martin Wiese. I will provide some example tasks and challenges that are more specific to my research project. A grocery store includes huge amount of items, which show huge variety in many aspects as size, shape, texture, fragility, and weight. As Martin's examples, when it comes to fruits and vegetables, even with the same object, we have huge variations. Or consider a shelf stocking task, or unpacking items from a box. The knowledge available to the sensors of the robot is very limited in both cases. How many objects are already in the shelf is not known and cannot be observed. Another example is packing items to a larger container. This task requires gentle manipulation of the items. Additionally, all of these tasks require precise control of the robot in limited areas, sometimes shared with humans. Object manipulation is the result of robot actions. The actions are the way the robot changes its environment by means of physical interaction, just like humans. Consider yourself trying to hold a cup. Where you hold the cup depends on the properties of it. Does it have a handle or not? If so, where is the handle? Humans can solve this kind of problems very fast, thanks to their advanced brains, hands, skins, and years of interaction experience with the surroundings. Inspired from the humans, my current research is on enabling the robots to make these kind of decisions in a store accurately. These decisions require the robots to learn to relate what they do, which objects they interact with, and what is the result of these actions on those objects. In this way, the robots can develop a forward model that is the understanding of outcome of its actions in an environment. If the learned forward model is good quality, then the outcome predictions can also be used to choose actions or action parameters for next times. I'm going to present two different use cases of my research. The first is learning grasp strategies on challenging objects, and the second is shelf stocking task. For grasp learning of complex objects, we choose bananas as use case. The reason is that bananas are in irregular shape, that they do not include symmetry. They show variety in geometry as shape and size. They are deformable, but mostly the deformation is not wanted as it fastens the rotting process. And we can separate the bananas to individual fingers from their crown. The motivation behind this use case is that if the effect of differently parameterized grasps can be predicted, then the selection of actions can be more conscious for changing goals. For example, the goal can be getting a single banana or carrying the hand of banana together. But first, which actions cause that separation should be investigated. We initially developed the model of the bananas in simulation environment. In order to have initial algorithms running, the simulation speeds up our data collection part. Additionally, we avoid wasting real bananas. In the video, you see some examples of different grasp actions on various models. How many models are there? How the bananas are placed in the environment? Where the grasp is applied all have impact on the results. The second use case I will talk about is shelf stocking task, which is the subject of master thesis of Arthur Helslow. The challenge with this task is due to the limitation of sight, because only the front view is available. Therefore, when the robot sees an object on a shelf, it cannot know whether there is only one object or there is more behind it. The robot should infer how full the rows of the shelf are while stocking by combining its knowledge about objects, its observations, and the effect of its actions, and plan its next actions with the understanding it develops. Here is an example execution from the experiments. The robot here is stocking a shelf that is partially full. The robot uses push and place actions to change the shelf organization. As shown, it infers to place a product when it sees an empty spot in front part of the shelf, or pushing if the front shelf is occupied to open space for another product. It also infers existence of an object it has never seen, as it's hidden behind other objects, with reasoning about its action results. As a team, we are going to keep working on improving the intelligence of the robots for retail, and wish to share our new findings.